Okay, we'll now go back to the user presentation. Alex Nelsonville from R. So I'll hand over to Alex. Thank you.
Okay, thank you. So I'm from the Processor Division in Cambridge. The title of this presentation is Leaving the Nest, and this is sort of an allusion to the fact that formal is often seen as a sort of chicken and egg thing. But these birds here are actually pelicans, and I'll talk a little bit about what pelican is in a moment. So a little bit about me. I've been using formal for 10 years, and I've worked on various cores. I'm not from an academic background, so my appreciation of formal is very much from an industry and sort of execute on projects perspective. So the current project I'm working on is actually called Pelican. It's an unannounced product that ARM is working on. This presentation talks actually about formal from the perspective of this particular project. And there's no information obviously in this presentation today about actually what Pelican is. So I'm going to just very quickly just sort of point at this slide and say we all kind of know these issues with are the levels okay on my mic, by the way? Yeah? Okay, good. Yeah, so these are kind of the sort of issues that we've seen. And I guess the key point here for us is that very much there's a renaissance sort of happening within, I guess, ARM at least. I don't know about the whole of the IP industry. I hope it's in the IP industry. But the formal is starting to become, for us at least, the next constrained random. And this is an interesting metrics slide that we had lying around. Some information here about actually assertion density. And this top graph shows what you could probably interpret as just different attitudes towards formal. So here we've got a block at the bottom which has very shallow, if any, density at all in properties. And as you go up, obviously, so this could potentially indicate that there's a sort of different attitude towards using formal. And along the bottom here, we've got what looks like a sort of typical project timeline and various properties, or at least the status of properties in a given project design. And I'd say that in the early 2000s, we probably reached this stage here where we may have explained away certain fails. Usually our constraints weren't very good, and often these things can be paled into under constraint. So very much nowadays we're in this sort of region here where we're effectively in a world where we have no failures left. We're basically all proven or undetermined. And the whole idea here is now we're trying to move very much into getting all of the properties into this determined and proven area. And it's obviously a very difficult thing to do. But attitudes have turned around for us almost 180 degrees. And the solution to this adoption problem for us has been largely around actually high-level management buying into formal as a technology. And the only way that this could happen was to use evidence from past successes to make our arguments. So in terms of Pelican, these high-level managers resourced a team, quite a substantial team actually in Cambridge, and ring-fenced it for formal on Pelican. And so our stat, there are other stats from other companies, our stat is 17% of the Cambridge Pelican team is working exclusively on formal. And this is not just a certain class of engineer, this is from veterans to grads, so we're also bringing in the next generations. And Pelican is doing mainstream and deep activities. They're both resourced equally, and crucially this equal resourcing includes block designers having time specifically allotted in the plan for them to actually do formal. So separately to this, so ARM has quite a regular global verification conference, and usually over 100 engineers come to this. And at the last one, formal came out very much fighting. It was almost unexpected, to be honest. And of course, there are other structural or infrastructural things that we're doing as well to take advantage of. So, for example, we've installed a big shiny new cluster in a shed out in the car park, and we keep track of tool issues in an efficient way. So, whenever we find things, we can then share that with other formal users. And we're also developing a community around formal. Every couple of weeks, we meet, talk about formal. And this has helped the adoption to sort of percolate through. And things that we had in hand, so past successes that I talked about, we have an interface specification methodology, and I'm saying version 1 here because I'm going to talk a little bit in a minute about sort of a version 2 and sort of what the collective of version 1 and version 2 actually says and what it buys us. And ARM is quite expert at X propagation analysis. We've done some quite Herculean efforts on X analysis, actually, where we dual instantiate the design to check that the design is actually deterministic by proving that the outputs are the same when you compare the design to itself. And I would urge anybody, if they're interested in papers on X, some of the ones that came out of ARM in the early 2000s were Mike Turpin's papers, which were presented at SNUG in 2003 and 2005. The first one is called Dangers of Living with an X. It's quite a good paper. I would urge you to read it if you haven't already. Yeah, it's very good. And invariant analysis techniques. So this is a way of us effectively stating what the reachable state space of the design is and proving this exhaustively. And we have various flows inductively and from reset. An interesting fact here on this slide is the Cortex M0 Plus had a sort of gigantic multi-hundred-line statement which talks about the reachable state space of the design. Which I haven't got a code shot here for you, but someone else used one in the slide once, and it was pretty impressive. So in terms of interface specifications, large designs have a lot of interfaces flying around inside them. And really, you do need to know how your interfaces should operate. And so we have a specification flow which effectively allows the designer to dump out a module which then is instantiated between the functional units in the design. And we have an in-house tool chain. So we have parsers, elaborators, renderers, and so on. And this methodology allows us to create the way that it's specified is to create a expressive language on top of Verilog. So there are certain parts of the syntax definition where actually Verilog can live. So we can embed stuff inside this. And it also goes ahead and creates implicit property checks for different flows. So an example here, we were asked, well, we're working on this in flight at the moment, this version 2 on Pelican. And one of the simulation engineers came to us and said, I don't actually know how to check that my BFMs are always driving X when interfaces are not valid. So one of the things here that we have added as a thing we're going to render is checkers for simulation BFMs so that the simulation guys can also benefit from this. And we have a simplified assertion syntax on the front end in the ISL, which then we render out as either OVL or SVA or Pickle or PSL. The whole list is there. And here's an example syntax where looks like any sort of syntax really that you define to say, here's an assertion. Let's push this. Another thing that we've developed that kind of goes hand in hand with these interface specs is a hierarchical proof manager, which this is kind of a complex slide, but I can basically summarize it as within the context of the top level, we may have undetermined properties, and we would ideally like to do block level verification, but in the context of that top level instead of creating different environments. So this proof manager harnesses these interface specifications and allows you to do a compositional analysis. So this could be this could be anything, right? But let's say, for example, there's a little bug hiding in block A. Then if you were to run at a top level, it would remain undetermined, the properties around that. But if you compose a subsystem, we can also observe these bugs. And this also helps us to check for things like over or under constraint, because obviously the behaviors here, the intersection of these compositions will allow us to identify these things. And we can, of course, harness this in our X propagation and auto check analysis and some of these other flows. So another level of analysis that's been done on Pelican is at the architecture level. So if I don't know how many of you have read the ARM, whether or not you've looked in it. It's 2,500, 3,000 pages of stuff, but crucially in it is embedded some pseudocode. And that pseudocode is sort of executable. I say that. I mean, you can observe here that I've got some revisits, and crucially, there's this word accompanying the revisit, unpredictable. So there is some non-determinism in the architecture. And we're able to highlight that non-determinism in this model, which I've converted from this pseudocode into a sort of high-level system Verilog specification. And this executes next to the memory protection unit. So the example here is around the PMSA and the memory protection unit on Pelican. And I'm quite pleased to say that actually for the predictable space of the architecture, we've been able to close out an exhaustive proof on this. So we actually know that the behavior is kosher with respect to the actual architecture specification here. And there's just some example code here. Crucially here, we had some problems actually using the formal tools, some of the Verilog structures and function calls and so on, and all of the tools. So I think there was no tool that didn't have a problem with this, either in the behavior or in the things that it would accept in terms of compilation. Obviously, I didn't try all formal tools, but the ones that we did try had problems. So I spoke earlier about this deep activity. So we're doing mainstream, which I believe the interface specifications fall under. And we're doing what we're calling deep formal, which is memory system verification. And this comes in sort of 4 phases. I'm not myself working on this, so I'm not exactly sure which phase we're actually in at the moment on Pelican. I think we're approximately somewhere floating around 2, 3, or intending to get to 4. And this is about effectively creating a microarchitectural specification of what the architecture defines as memory system behavior. So ARM has a very weak memory ordering scheme. And the whole attempt here is to capture these things actually. I'm going to show you a slide, actually. I'm going to go right to the back here. So we call this thing a directed observer graph. This kind of describes, I'm not going to go into the detail. I don't understand this slide. I got this from someone else. But this thing effectively defines an end-to-end behavior of the memory system. This is one of the most basic ones we have. We have many more diagrams like this, some far more complicated. And we call these dogs, and I suggested to them, this is a bit of piffle, but I did suggest to the guy actually that, the language in which he describes dogs should be called woof, but he kind of didn't accept that. They called it polos instead. I don't know why. So the next thing to do, obviously, is to write properties, end-to-end properties on this specification and prove those on that specification from 1. And then we need to refine this abstract spec down onto the RTL. And crucially, when we start to operate this thing in the formal tool, we'll be making use of also the designer properties to support the invariant around this. And then we finally go to a proof stage where instead of writing the end-to-end properties on the RTL, we simply prove that the RTL implements the abstract specification. And that avoids the need to write these complicated end-to-end properties on a much larger design. We just need to get equivalence with the abstract spec. So there's been talk in the room about bugs and analysis, and ARM agrees that formal verification is a very good bug analysis tool. And what tends to happen with us, wherever an errata may fly in from, we would leverage not just formal, so we will also use other techniques, but formal seems to be the best technology here. And what it leads us to do is, when we find the bug, this little bang here, we then write these satellite properties around that area as well, and then we try to prove those as well, to do the diligent thing and to make sure that there's no further issues in these areas. And I think almost universally we've had 100% success rate doing this, at least within PD. I don't know what other, so processor division, I'm not sure what other divisions do. And so this is my slide of sort of bag of bits, I guess, as a message to sort of EDA of those sort of things that are important to us. Certainly language support, so the experience at least that I had with the various tools in implementing the architecture spec for the memory protection unit, language support is very important. And we're not just in sort of vanilla RTL mode anymore. We're doing complex stuff with fairly high-level structures in system Verilog. And of course, focusing on user interaction, there are some tools we'd love to use more, but because their interfaces are not quite tuned for the sort of style of debug that Formal requires, they've come more from a simulation aspect, we would urge work in this area. And of course, some of the flows that we work on internally sometimes require a command that, for example, is not available, or we do a lot of sort of design crawling type stuff, and it would be very nice to, to have a more, whatever the opposite of conservative is, liberal approach to providing commands to us. So for us, for me, in summary, Formal is not just a niche topic anymore. So on Pelican, we're kind of building it, and we've gained the adoption of designers by putting the effort into the methodologies. And finally, bug avoidance and hunting flows are very much leading the proliferation of Formal within the company. And I think that's it.
Thank you very much.
Thank you.
Oh, leave your questions to the back.
We haven't talked about coverage. When do you decide to close?
Are you talking about Formal coverage?
Yeah, when you're using Formal, right, for certain types of verification problems in Pelican, as you said.
Yes.
So when do you decide it's enough?
So I haven't gone into metrics here, and that's a very good question. When do you decide it's enough? I think I'll chat to you about this separately. It's a perennial question. I don't think anyone in this room really has the full answer to this, but we know that we do a lot. Okay, so we know that we're doing a lot of different aspects of Formal. We're putting in the interface specifications. We're running the different flows, and with all of those things in hand, plus of course the thing that I don't mention here is that we have teams doing simulation alongside this Formal team on Pelican. So I think we got the basis covered. But in terms of actual metrics, we discuss this a lot, and it's a perennial question that we do have. We have flows that will render metrics. Whether or not they're the right metrics is open to question.
Yeah, I guess my question is more on the
So my thoughts are that I'm hoping the EDA guys in the audience are going to help us solve this problem. I mean, my push would obviously be, I agree I don't mention it in this presentation, but yes, we all need to work together to hammer down on this metrics problem.
Yeah, I mean, obviously, when Anthony gives his talk, you will know what we've been trying to do with imagination.
Sure.
At least one of the things that we're trying to do, but just wanted to know your thought, because you guys seem to be doing quite advanced Formal on a live project, with a significant commitment of resources. There has to be a measure of, have we fucked up,
Yeah. Yes, to pardon your phrase for you. Yeah, exactly. So some of these techniques are, as I said about, for example, the deep Formal. Oh, where did that go? Oh, I must have gone the wrong way. So for the deep Formal, we are kind of floating around in this stage where we're not yet realizing the full benefits of this. So metrics kind of for this activity are not only difficult, but we're not at the stage to collect them yet. In terms of interfaces, obviously we keep track of how many we prove, how many we don't, the usual metrics. But again, this presentation isn't about metrics. This presentation is about the actual work we're doing. I suspect if I went and dug, around the sort of various teams, we would find lots of interesting thought on metrics. And yeah, so we certainly do use Formal to cover the unreachables from simulation, or to prove that simulation holes are unreachable.
Okay, thank you very much, Alex. Thank you.
Thank you.